Okay. All right, so we're moving on in the book to chapter 6. And I don't know, I guess, did we talk about par last time? Anyone?
I don't think so.
Ah, right. Last time I told you about the work that we were doing. So let me finish up with par before we get to go on to chapter 6. I'm gonna have to. I'm trying to find my notes. Let's see. There it is. Right. Okay. Well, those of you who put pictures up, thanks. Let's see. Share screen. All right. Right. So last time we talked about abstraction and kind of layers of abstraction and how that's a standard. I mean, that's how we, that's the main tool that we use to kind of like control the overall complexity of systems. So we try to isolate issues below a certain level. Like when you're writing a program, you never have to worry about the operating system handles memory management, even though multiple programs may be running at the same time on your computer. The abstraction for each individual process or each individual program that's running is, I have my own memory space. That's a really useful one. Okay, so let's look at par, though. This is a parallel operator, which is a little different from the non-deterministic or that we looked at last time. And so I don't understand why it's not letting me make this thing larger. I can make it to full screen, but can you see the writing over here? I think my problem is it gets bigger on these notes down here. Well, hopefully you can read this. So it says, all right, we'll consider how to add a concurrency operator, par. And so the new syntax for statements includes, all the old ones, assignment and skip and if and while and the S1 or S2 and this S1 par S2. So remember, the OR operator adds a non-deterministic point by, it's kind of like a branching point. You could do one or you could do the other. And so we had, like in the small step semantics, S1 or S2 could evaluate to do S1 in state S, which was the state here, or again, as an alternative, S1 or S2 in state S could evaluate in the small step to S2 in S. And so the OR is just kind of like a non-deterministic choice between these two elements. The par operator interleaves the evaluation of statements S1 and S2. So if S1 and S2 are statements that have semicolons in them, then they're complex. They have multiple parts to them. And what these rules do is they allow you to interleave the behavior of S1 and S2. That is hard to see. I wonder if this could, I don't know, this is a silly idea, but maybe I can take a screenshot of that. Oh, but where did it go? I think it goes to, let's see. Oh, maybe it goes to pictures, probably. Well, there's screenshots there, but not the one I want. Oh, all right, whatever. I mean, you can look in your book. I think everyone has a copy of the book. This is on page 77. So this is the rules on page 77. And the first one is saying, if you have S1 par S2 in state S, then you could choose to evaluate S1 in state S, and that would give you S prime in some state S prime. And now this par becomes S1 prime, that one. S2 doesn't change, and S prime. So you've executed sort of one statement sequentially from S1. But now suppose that when you execute one statement from S1, it's the end of like a semicolon sequence. It evaluates to a final state. And so then you've got this state S prime. Well, now you could just evaluate S2 in that state S prime. And then you have a completely symmetric set of rules for evaluating S2. You could evaluate S2, well, the par of S1 and S2 in state S, by choosing to evaluate S2 in state S. And if that leads a new program state, which is a pair, S2 prime, then you evaluate S1 par S2 prime in the new state S prime. But similarly, if you sort of run out of evaluation to do in S2, you evaluate to a final state, then you just complete S1. So here's the rules. This looks similar to semicolon, right? In S, except that the way that you get to evaluate S2 is only after you've evaluated all of S1 in the semicolon. So if it's S1 comes before S2, you evaluate S1 until there's nothing nothing left. You get down to S prime, and now you start evaluating S2. Whereas here you have these extra rules that allow you to evaluate S2. And so this is essentially saying evaluate these two programs in parallel. And so as an example, you could say, okay, X gets the value of 0. Par, X gets the value of 1, followed by X gets the value of X plus 2. Now, there's, using the rules above, there's a number of different ways to evaluate this. And I think I wrote them all down here. So this, if I choose to evaluate S2, then I end up evaluating, well, this is with, I'm sorry, this is a par. Let me try writing it myself again, because this is from some older notes. Except where is my Wacom? Okay. Okay, so suppose that we've got this is S1 and this is S2. Then, so we'll start out and we'll say, okay, X gets the value of 0, par, X gets the value of 1, followed by X gets the value of X plus 2. Now, what are the possible, in state, some state S. Now, you notice that it doesn't kind of matter what the state is, whether or not, X has been defined before or not. Because by the time you get here, X will have been given a value in the store. So remember, for us here, I'm saying store, and that's from the next chapter. Really what I mean is state. So this is the state. And that's a function that maps variables to ints. Okay, so now there's two ways this could go. One way is by the rule par 1, and it's going to turn out that par 1, you got to use, sorry, they're numbered 1, 2, 3, 4. This is actually the rule par 2. So by par 2, small step semantics, this evaluates to Now, because on the side, we show that, okay, x0, x gets the value of 0, evaluates, well, let's see. So let me draw out the derivation. So we've got, this is our S1 and this is our S2. And so by the rule, when I look at this, this is going to evaluate in one step to a state, right? So x gets the value of 0 in state S, evaluates to, in one small step, S, where x has the value 0. That's just the rule. And so that means that if I just call this S1 par S2, that, and I'm evaluating in the, starting out in state S, that evaluates to evaluate, let me make that a little bit clearer, move it out, S2. The new rule, the rule says, oh, then evaluate S2 in the state S where X has the value 0. So that's one step. So that means this could go in one step to this. But I could have selected the other rule for I could have selected the rule to try to evaluate on the right side of the par statement. And if I did that one, then it can't be this one because I can see that this statement is complex. It's got semicolons. So it's not going to go in one step. So there's this rule would work. So now we can either, this one we can continue, and there's no more pars in here. So this thing just evaluates to x gets the value of x plus 2. Let me move my display over. Comma. And now we've got x has the value 1. So we have whatever the original state was with x getting the value 1. And now when I evaluate this one, because x gets the value of x plus 2, would look up the value of x against 1, and so then I evaluate just to a state where x has the value 3. So when we chose, this was par 2 rule. Once we evaluated this, we had no non-determinism left. So let's start again. Let's see what happens if we went with S1 par S2 starting in state S. And instead I say, oh, let's evaluate this one, the one that is S2, which is x gets the value of 1, followed by x gets the value of x plus 2 and evaluate that in state S, and that evaluates to x gets the value of x plus 2 because I'm not done yet, but evaluate that in the state S where x has the value 1. And so that means that this thing down here goes to S1 par x gets the value of x plus 2 in the state where x has the value 1. But now there's a par again, so now I could choose the left or the right. And in the end, the possible interleavings of these things. So these things, this rule doesn't allow you to change the order of semicolons. So there's no way that you can evaluate x gets the value of x plus 2 as the first thing that you do. So the first thing that you do is you either evaluate x gets the value of 0. And now I have to, there's no more parallelism. So now I evaluate x. I didn't mean to write right on top of myself. X gets a value of 1, and then x gets the value of x plus 2. Oh, come on. But it's also possible to choose the right-hand side first. And so the first statement that you evaluate is x gets the value of 0. And now there's two possibilities. One is that, oh, I'm sorry, that should be the 1. If I evaluate the right side first. Now, in one case, I could evaluate x gets the value of 0, so I could do the left side now, and then to finish it up, I'd have to do x equals x plus 2. Or I could do the second statement on the right side and say, okay, x gets the value of x plus 2. Oh, and finally go back and do the, use this rule to finish up with x gets the value of 0. So these are like the 3 programs that you could think of, linear programs or sequential programs. But what happens at the end is that at the end of this one, you get a state where x has the value 3. This one, you have a state where s has the value, x has the value 2. And in this one, you have a state, the final state says x gets the value of 0. So this is the problem with parallel evaluation, is you'd like your program to be deterministic. And in a later chapter, he talks about these operators for essentially making certain things atomic, which gives you the possibility of controlling the order, but also taking advantage of parallelism. So it turns out that this program here, this program here is equivalent to this program, or this, where there's semicolons, or this program, or this program. Okay? Questions? So this model makes it look like this model is like if you had sort of two programs you want to run in parallel, and you have them stacked as a deck of cards, with the top card representing the first statement in the program, and the next card in each pile representing the second, and so forth. And now all possible shufflings of those two decks is what you get as far as the possible interleavings of these programs. Now, you go like, wait a minute. I mean, so one is I completely run the first program and then I completely run the second program. That's not a very good shuffle, right? You would say, oh, that's not random enough, but that's one possible interleaving that you could get. And another one is you completely run S2. That's what this one here is. Here's the one where you completely run S1 and then you run S2. Here's the one where you completely run S2 and then you run S1. And here's the one where you start with S2, then you run S1 for a step, and then you finish by finishing out running S2. Questions? Come on, somebody say something. That's probably what I was doing here. This is like the same evaluation I just did over here.
It makes sense to me.
Now, since we ended up, and I kind of erased those things over here, but I had down here, okay, this is the state where x is equal to 3, and this is the state where x is equal to 2, and this is the state where x is equal to 0. You could also say what I said here is that x gets the value of 0 par, x gets the value of 1 semicolon, x gets the value of 2 is similar. And so that means, remember that in every state that I run this, I get to this. If I run this one starting in the same state, I get to the same output, essentially, to the same final state. And what's this one? This is the one that just jumps to the chase and says, oh, here, executing this one, you get x gets the value 0. Executing this one, you get the x gets the value 2. Executing the other one, you get x gets the value 3. Now, one of the exercises that he has in there is he says, like, okay, all right, if nobody has a question, I'm going to erase all this stuff that I've written here. Questions? Come on, somebody. So this models, threaded evaluation or concurrent evaluation of your program. So this says, like, okay, What was I doing here? Okay, suggest an alternative that allows progress by both S1 and S2. So it seems like you have to like flop around and write down a whole bunch of rules like this. Except that here, I'm missing something got erased this from the notes. This should be here. What should be in here is this is S prime. So that's what you got here. And it should be this plus union S double prime. And this one is equal, where this, so remember, this is a function from var to int. This is a function from var to int. So here I defined a kind of union of two functions where the new function is you take every variable and then you choose randomly either what you got from S prime. Well, so this is S plus union S prime. Up here, though, I want to like blend this function with this function. And so then you can say, okay, take S and S prime, and the new function is going to map X to whatever I choose, whatever X and X prime is going to do. So at whatever S is going to do, I choose that, or I choose what S prime is going to do, and I make that the value V. That's V is equal to the choice. And I don't know. I mean, this is a solution to this. You kind of mix them back together. And the thing is that for almost everything, S prime and S double prime are going to match on almost everything. The only case where they're going to be different is where you got one step from here to here, and it was something like, you know, you might have something like X gets the value of 0 par X gets the value of 1 in state S. And so by this, well, I would probably want another version of this rule where I also have the possibility of evaluating S1 to the end. So this is just a state S prime. And then I'd need another rule where this one is just a state. And then I'd need another rule where they both evaluate to just a state. But the bottom would kind of like be very similar on all three of these rules. So let's say we had those extra rules. I don't know if you're questioning what am I talking about. But if I say like here, okay, X gets the value of 0, or X is assigned the value of 0 in state S. That evaluates to S where X, oh, I forgot. He writes this, doesn't he? I've been writing that bracket colon equals. And over here, x gets the value of 1, comma, s, because here I start with the same. This prime should not be there, I don't think, if I'm going to do it this way. Because everything will be built into S double prime here. All right, so maybe I should leave this as a homework exercise. All right, here's the other rules. This one says, let me erase some of this stuff. This one evaluates to a pair, and this one evaluates to completion. See, this is right. This is wrong up here. This the top rule here should say, start with S to evaluate S1, and then start with S. Get rid of that prime. Start with S to evaluate S2. And then you're kind of like gluing the two resulting states together. And if they match on some input, then you have to choose. So like here, that's what I was trying to do on this, but here's the other rules. So the rule that I'm using is this one. Maybe if I scroll it up enough. Oh, good. Okay, so this is the rule I'm using. So X gets the value 0 in state S, evaluates to a new state where X has the value 0. X gets the value of 1 in the original state S, evaluates to what? Somebody tell me, show me you're not sleeping. Does anyone know? I mean, it could be I'm just like talking to myself the whole time. What does X gets the value of 1 in state S evaluate to?
State where X arrow is 1.
Yeah. Okay.
X bracket. Or yeah.
All right. Thank you. And so now then down here, if I call that, so now I take S and I've got X gets the value 0 in that one, and I plus union that with this one, which says S, X gets the value 1. And by that definition above of the union operator, these are going to match S. This S and this S are identical for every X, every input except this one X. That one they differ on. So this one, this thing here, depending on what the non-deterministic choice does, this thing here either evaluates to S where X gets the value 1 or S where X gets the value 2. So like, for this one, if I put in y as an input, this thing is a function, takes y, looks and checks, is it x? If it's x, it returns 1. If it's not, it does s of y. So this is just s of y. And if I take this one and I apply it to y, I get back s of y. So on every y that's not x, these two things are equal. Because that's the definition of what it means to do the pointwise function update. So I don't know, that's one way to solve this, is to try to like essentially push it into the semantics and deal with trying to glue together two different states. Now, you could write a lot more rules, and so I think you'd have to have, so we have 4 rules, right, to try to model this thing. We have this rule where they both have more to do. After I evaluate S1 and after I evaluate S2, there's still more to do. These other rules are saying, okay, oh, S2 completed, but S1 didn't. Okay, so then I do this. This one says, oh, S1 completed, but S2 didn't. Then I do this. Then this rule is the case that we had here, where S1 completes and S2 completes, and so now I do this. But I'm thinking like another way to do this is to, like, this one rule could become multiple rules. Like what we're trying to model is the parallel evaluation, but where you could take steps in both things, right? The original rules up here from the book, these rules only allow you to take one step on S1 and one step on S2. And now then the question was, can we design rules that will allow us to take multiple steps? And what I'm trying to say here is that we could rewrite, for example, this rule as 2 different rules. We could rewrite it as, so to take care of the other possibilities, kind of like this union operator here is requiring non-deterministic choice in it. And you might not like that, but it might be okay. You flip a coin and choose one or the other, but to decide what the resulting function is. But in this one, you could do it so that it's all built into the computation. So you could have 2 rules and so one of them could say, okay, S1 comma S evaluates to S1 prime comma S prime. And now use S prime to evaluate S2. And S2 in this rule completes. So I'm going to say that evaluates to S double prime. Oh, sorry. And so then finally, I'm going to say, okay, that evaluates to S double prime, but I need to allow for the other possibilities. So then I say S2 comma S evaluates to S prime. And now I evaluate a step of S1 in state S prime. And that evaluates to some S double prime. And the bottom of this is the same as the one above. And so this one evaluates to, oh wait, it was S1 is the one that, oh, so this one, I'm sorry, this one does not complete. It goes to S1 prime, comma, S double prime. And so now what we have is we have this evaluates to S1 prime, comma, S double prime. And so up here, I should do the same thing. I made a mistake here. This should be S1 prime, comma, S double prime. So these two rules account for the possibility of this choice operator having to actually choose something. And then if you do it this way, and you both S1 and S2 happen to change some variable, the same variable to different values, then you are guaranteed that in this, plus union operator, you're going to have to choose either, that X is 0 or that X is 1. And on all other inputs, everything else you look at, for example, Y, that's not the same as X, you get the same thing. In a way, I found it a little bit strange that he added this at the end of this chapter. He added this parallel OR, and he added the par statement to the end of the chapter. And it really, and then we're going to go back to studying the sequential programming language now. And then we do recursive and non-recursive procedure calls. And then I think after that, he introduces the rules for this new system called CC. I'm not sure actually which one it's CCS or is it, it's similar to something made in the 80s by Robin Milner called CCS, or a similar kind of notation made by Tony Hoare called CSP. So he says these are similar languages that he's going to present, but that's in chapter 8. And then we'll come back to more of this stuff, and there'll be, I hope, in there, I think in there, there's going to be some examples you can. So anyway, hopefully we get to that. Thoughts on this? Comments? Okay, so I don't know. Here I was saying something about in the lecture when I gave this last year. Um, so write S down arrow X to mean that X is defined in the state. Now, that's true if we pick states to be total functions, then every variable has a definition. But in a real programming language, actually, you kind of, you don't really use a function. We're going to use memory locations, and it's going to be mapping, if memory can hold, 1K bytes of memory we have, then if you address over that, we have to choose something to do. Either it's undefined and the program halts, you're out of your memory space, or if you try to address past it, maybe we wrap around. But one thing you could do here is you can make a function, the union of two. You could make kind of a non-deterministic function, and you could look at it. You could say, okay, look, if X and Y are variables, and S and S prime are states, then if X is not defined in S and Y is not defined in S, then the result of this is the empty set. So you can think of, it's perfectly okay mathematically to think of collections of values as your values. If you take 4200, I think you do this. You talk about non-deterministic finite state machines, and then you do the so-called subset construction to turn a non-deterministic finite state machine into a state machine. You just make up new states, which are subsets of the original states. So this one would be everything's undefined. If X is not defined, but Y is defined to be K, then make it K. If Y is not defined, but X is defined, okay, just make it whatever X was. And if they're both defined, just make it the two of them. And then if you want to do that choice function, to choose just one of those, you choose then is a function from subsets of Z onto single integers. And so here you would say, okay, choose K would be K. There's only one thing to choose. There's only one thing to choose. Here, there's nothing to choose. That's undefined. But here you could choose J or K. And then the property would be that, if you choose something from X, if that's equal to V, then V better be in X. So in other words, if I choose from JK, then the thing that I choose better be in there. Now, what if you have a partial function? And this is actually like an issue in this programming language work that we're doing. Identifiers are only kind of like defined if they've been declared in a way, or if they've been, I could write the example here is, what if Y is undefined? And I say, X gets the value of Y in state S. Well, what am I supposed to do? I mean, the regular answer is that, okay, you take S and you evaluate whatever Y is in state S, you get back some value V, and so now you have a new state where X gets the value V, whatever value Y had. But what if your states are partial? In other words, it could be that Y is not defined. Suppose Y is not defined in S, then I would think that you should probably allow a terminal state like this. You can't evaluate this assignment here because you don't know what Y is. Now, it's interesting that this comes up, this exact problem comes up in the language that we were talking about last time, where we have this language called Faustus, which is our extended language. And so there's Faustus. That's our language. And then there's Marlowe. Marlowe wrote Faustus. And in Marlowe, it's possible to refer to a name that's not yet bound. And so what they do is they say, okay, look, their rule would be something like this. It would say, okay, X gets the value of Y, and this is if, Y is not bound in S. And in a way, it doesn't seem like a great, I mean, I would think like, you might say in this case, look up X. I mean, what are the things you could do? What they do in Marlowe is they say, oh, evaluate to a state. If Y is not bound when we try to look it up, just go to a state where X gets the value of 0. And so it's like a random value. So this is if Y is not bound. It says, okay, just everything that's not bound is 0. And that's what they did in the Marlowe compiler. And I really object to it. I mean, I think, one thing that might be better is to leave X unchanged. Say Y is meaningless, so this is sign. So you could say, you could make it a no-op. Okay, let's see. It looks like I'm almost out of time, huh? Oh no, still got some time. The thing covers up my clock and I can't seem to move it out of the way. Ah, except I have a watch on, don't I? My old watch wasn't working. I had to send it in to be repaired. Okay, so that's like an introduction to this kind of ideas of introducing non-determinism. So what we're going to do next, and I mean, we have what, 15 minutes. I can, at least give you an introduction, and you should read chapter 6 on blocks and procedures. But so, are there any questions? Someone ask me a question.
I don't have any.
All right.
I actually had a question that was more related to the class rather than the like the topics you were talking about.
Uh-huh.
So I
Okay.
know you talked about it a little bit. I'm sorry. Go ahead.
Go ahead. No, I'm sorry. There's a lag.
No worries. No worries. So I know you talked about it a little bit last week, but I guess I just wanted to clarify. So what is the full official plan for our midterm exam?
I will release it. It will be released at midnight on or 12:01 a.m. on Thursday, and you'll have to hand it in by 11:59 p.m. on Thursday. So
Okay,
you
thank
have
you.
basically 24 hours to do it. But it should take hopefully, an hour and a half. Okay?
Okay. Thank you.
What kind of questions can we expect on this? Like what the formatting and such?
I haven't made it up yet.
Oh, okay.
What would you like to see? Would you like to see some Haskell programming questions? Like I give you some formal description of a little semantics and I say, okay, write an evaluator for this in Haskell. Would that be a good problem? Something like that. Or, here's a little semantics, do something different with it. I don't know. Like you had an assignment where you had to make the small step semantics deterministic. One thing I haven't looked at, I got a strange email the other day that said that Finley had been added to the course as a TA, and I thought he was added from the beginning. Does that mean, does anyone go to Finley for office hours?
Yeah, I've been to his office hours.
Okay. And has he been grading the homework? Because I haven't looked at that.
Yes, he's been grading it as far as I know.
Okay. Because I'm thinking, I don't know why I got this email like last week, the end of last week, saying something like, Finley McElwain has been added as a TA to COSI 4780. And I'm like, what? I thought he was doing that the entire semester. But maybe they just sorted it out. It may have had something to do with his pay and not his access to the courts or something. I don't know. So, some other people have gone, Finn is great. I don't know. I think he's probably very helpful on this stuff, even though when he took this course, this was not the material we covered. You know, so if you have questions, so maybe I should be, I don't know, making like a bigger project for this class. What can I do to engage you more? Anything? I know some of you are actually kind of interested in the material. Like what, you know, what would you like to see? I mean, we have to do chapter 6. And actually, the beginning of chapter 7 at least, probably all of chapter 7. And then, oh, then he had chapter 8. And I think I skipped chapter 8 last time to be able to do chapter 9, which is how do you implement or records and how do you describe them in the semantics. That's kind of cool because it's a very generic implementation of that you can use for lots of hierarchical structure, right? A record can contain as one of its fields a record. And so then, you know, if you use like the kind of standard dot notation, you know, R1 dot and then R2 dot, and so you can get down through the fields that way. And so we actually implement that one. And then once you have that, you can start to sort of talk about objects. And so we could continue that way, or we could try. Yeah, and I didn't really get to blocks, but I mean, they're actually a trivial extension of what once you have all that other stuff. So I don't know if anyone has a preference, send me an email or okay, Jessa is asking, can we incorporate some lambda concepts from the stuff from the lambda calculus into what we're learning? Actually, that's chapter 12. Which I don't know that we can get to chapter 12, but there is a description of lambda calculus in chapter 12. So the lambda calculus is more for functional languages, but we could add, like, I mean, now Java and C++ and, oh God, I don't know, Python and everybody has some kind of lambda now. So we could see, how do we what are the semantics of lambdas? We could do that. That would be fun. That might be an interesting little project to see how do you implement that feature, which is, I think, a little bit mysterious to a lot of students and, you know, maybe even some faculty. I don't know. It's only recently that it's been added. I heard Kim Buckner say something like, just stay away from it. Something like that in C++. I don't know. Is anyone programming in their imperative programming languages and using lambdas or closures, or they call them different things in different languages? Does everyone know what it is? Probably not. So, I mean, a lambda expression is just a way. So in a programming language, whenever we write, let me go back to the, I'll go to the whiteboard for a minute. Whenever we have, oh, we've only got a couple of minutes here, right? So whenever we have something, you know, whenever we write down a function, we say something like, you know, there's some keyword or something like fun, and then F, and then maybe you give the arguments, and maybe you write down the types of the arguments, you know, and then you give the body of the function, and then you know, you end. I don't know, maybe we'll use the squiggly bracket notation here. So, but when you do this, what you're doing is you're binding a name to F. And what the lambda notation lets you do is make a function where you don't have to actually select a name. It's just a way of writing down an expression. So suppose, you know, I don't know, suppose this is some sequence of expressions in here. We'll just call it capital P. You could write down a similar thing, an almost identical thing. You could say F is equal to lambda, and oftentimes lambdas, but I don't think I need to look at them in some of these other languages. I haven't studied that, but you could do this. And so this is lambda, and then you could say, you know, P. So this thing here is an expression that evaluates to a function. Whoops. Oh, God. It's an expression that evaluates to a function without having to give a name to the function. And so if I wanted to, this should be semantically kind of the same thing as doing this and binding F to this lambda expression. So a lambda expression. Now, but what would we have to do? Well, class is over, I guess, but to do this, it's possible though that P down here, this P might contain, you know, this could come like I have some, you know, S1 semicolon, then S2 semicolon, then I have F equals this lambda, or I can just apply this lambda to some arguments of the right type. But it's possible that P might refer to like a variable declared earlier in the program. And so now what I'm going to have to do is I'm going to have to kind of like package up the things that I can need to evaluate this lambda when it's called, if it's called later. And that means kind of like that's what a closure is. A closure is the package that includes, okay, what is the stuff? Oh, this refers to a variable X that was declared here, and you know, what was the value of X at the time this lambda was declared is one way to do it. Or do you leave it dynamic and you say, okay, X is going to get the value later on, and it gets complicated for lambdas. But we'll see, first of all, what happens with regular things when we do that. Like we can declare procedure. We're going to declare procedures soon. And they have the same issue. Like, okay, which components in the procedure are like lexically scoped from, what's the scope of things that appear in a procedure definition. So anyway, that's sort of what we're going to start talking about next time, actually, on chapter 6. Well, first we're introducing memory and then procedure declarations. So that's what we'll probably get to next time. But we'll have an exam on Wednesday. No class on on Thursday. No class on Thursday. Any questions? All right. Well, I'll see you on Thursday.
Thank you.
All right. Bye.